Okay, so can you see the presentation?
Yeah.
Okay, so we stopped here last time on this slide. So Anirudh, we what we did was we you were not there. So what we covered last time was some guidelines and some information about synthesis. So after Verilog functional verification is over, you need to synthesize the design, and there are certain guidelines that you have to follow for synthesis, and there are certain optimizations that the synthesis tool carries out on your Verilog design, generate the gate level values. And after that, so actually synthesis is not part of this training, but I just wanted to cover that section just to give you idea about what synthesis tool does. And what we did after that was the compiler directives. The compiler directives is basically if you're done C programming, this is similar to what hash include or hash define statement does in C language. They are called compiler directives in C language. In Verilog, these are the compiler directives which has tick include, the backslash tick include, backslash tick as it's called. Tick include to tick include a file name, tick define. If you want to define a set of macro, tick if def, it's like if else if. And if. So those were the things that were covered. Um, any questions on anything so far?
No.
No.
So today we'll look at system task. So system task are tasks and functions used to generate input and output during simulation. Their name begins with a dollar sign. It's a dollar sign. The synthesis tool will parse it. Parse means it will read the system task and ignore it since they are used for simulation only. We can include it in synthesizable designs, but the synthesis tool will ignore it. Why? Because these are tasks which are meant to be used during simulation to perform a particular task or a function, like display a message, something along those lines. So there are few system tasks which will do a few activities. They can be used for simulation and ignore the synthesis tool. One first set of system tasks is dollar display, dollar stroke, dollar monitor. So they are each of these tasks will help us print a particular statement or display a particular message in the simulation window, and there are slight variations to each. So dollar display and dollar stroke will display once every time they are executed, whereas dollar monitor displays every time one of the parameter changes. So dollar monitor keeps running on in the background, and anytime one of the signal names that we want to display changes a value, the dollar monitor will display a updated message. Dollar display and dollar stroke will execute once when we execute this command, dollar display or dollar stroke. And dollar display and dollar stroke, there is a variation again. Difference between dollar display and dollar stroke is that dollar stroke displays a parameter at the very end of the current simulation time rather than when it is executed. And dollar display will immediately execute it, display a message as per whatever we are defining. We can display the message or display the values in one of the following formats. %D stands for decimal value. So if you want to display some signal name or signal value in decimal format, we have to use %D. %H for hexadecimal values, %B for binary values, %C for character, ASCII characters, just regular ABCD characters. %S for strings, %T for simulation time. And we can also display the hierarchy of the design using %M. So these are some of the formats that are supported. If you look at the syntax for this, now if I use this dollar display open parenthesis double quotes, the values of signal par1 and par2 are as follows, double quotes, comma par1 comma par2. So par1 is a signal or a register in Verilog, Or par 2 is a register or a wire. It can work on both. Par 2 is also a register or a wire. So first it will when we use dollar display, it will immediately execute this task. In the simulation window, it will show values of signals par 1 and par 2 are as follows. This message will be displayed followed by the two values. First of par 1 signal and second of par 2 signal. So this is very similar to printf statement in C language. If you use C language or any language for that matter, normally there is a printf or similar statement. So this is what it will do for us. It will display a message there. Dollar strobe would display this message followed by par 1 and par 2. Now the difference between dollar display and dollar strobe is dollar strobe will display a message at the end of the simulation. Whenever the simulation ends, it will show a display. It will show the message. Dollar display will immediately display it whenever we execute this command in the Verilog. Normally this is included in the test benches. So if we whenever we use it in the test bench, it will immediately show this one. Dollar monitor uh, double quote format strings par 1 par 2. So the way dollar monitor works is it keeps working in the background. Anytime any change in par 1 signal value or par 2 signal value, a new message will be displayed with the updated values in the simulation. So dollar monitor works on a continuous basis. Then there are certain variations of dollar display, dollar strobe. So dollar display B will display any values in binary format by default. Dollar strobe H will display the value at the simulation at the end of the simulation in hexadecimal format. So these are certain variations, but these are the main three tasks. These are system tasks, and anytime we have a dollar sign, it is a system task because it's a task used for simulation system, simulation software. Dollar display, dollar strobe, dollar monitor. Any questions on this?
No.
No.
So we'll go through the system task first, and then I'll give you time to note down the main points you see in the screen. So we'll see. We'll quickly go through this first. Then the next set of system task is dollar time, dollar s time, dollar real time. This returns the current simulation time as a 64-bit value, 32-bit value, and a real number. So 64-bit value when you use dollar time. Simulation time is the current. So when you run a simulation, you can, for certain reasons, you would like to check your time, how much time has passed, or you would like to even display the simulation time after every few stages of the test bench. For such cases, you can use this kind of this system task, which are dealing with simulation times. Dollar time will give me a 64-bit value, dollar s time will give me a 32-bit value, and dollar real time will give me a basically a fractional value. Real value means it's a fractional value, so 30.20 nanoseconds, so 50.10 microseconds. If I want to display that, I have to use dollar. Dollar reset, dollar stop, and dollar finish. This is a system task. Dollar reset will reset the simulation back to zero value. Dollar stop will hold the simulator and put it into interactive mode. Interactive mode means it will go to the command line of the simulator and the user can type in the commands. Dollar finish will exit the simulator back to the OS. Basically, it will finish the simulation and close the simulator. That's what dollar finish will do for you. Dollar reset, dollar stop, and dollar finish. Dollar random will help you generate a random number. So there are multiple times when you first of all, when you test any design, you would like to test as many random possible combinations as possible for all the input values. So you might, in certain cases, need a random numbers for that. Dollar random system task will help you generate a random number, and it will have one input which is called a seed value. So you seed is basically some value from which it starts. Internally, there is an algorithm which will help you generate. The simulator will generate a random number for you. That random number can be used for testing purpose. So the dollar random will be based on that. The next set of system tasks are no longer used, but they are there. Dollar dump file, dollar dump var, dump on, dump off, dump all. So many years ago, nowadays, if you see the simulator, it is all integrated as a part of one single software environment. It's all an integrated design environment or integrated system environment, whatever. So it's only one single software. Simulator, synthesis tool, then timing diagram generator, timing diagram display, everything is part of one software. Many years ago, 10, 15 years ago, they were all different softwares. So you had to compile, for example, you had to compile the Verilog code using compile and simulate it using a different software. Then you have to view the timing diagrams, generate the timing diagram, and view them using different softwares. For such cases, we had to use this system task where a dump file is basically after you compile and simulate the code, you can dump all the signals in something called a .vcd file. It's a value change data format. So it's a format where the various signal names and various transitions of signal from logic 1 to logic 0 were stored. And that file, we could save that file as some file name .vcd and then import that file into some other software where we wanted to view the timing diagram. So this is no longer applicable because all this stuff is integrated in a single software, so you don't have to store it somewhere then import it somewhere else. Everything is done automatically using the same software. But these are system tasks which are related to that, to basically save the signal simulation results. Dump file, dump var, dump on, dump off. $F open, $F close, $F display, F strobe, and F monitor. Each of these is a system task related to files, file IO operation, basically. So $F open will open a file and give the file a handle to be used by other commands. F close will close the file. So if you use a file IO operations in any language, have you used file IO operations in C language or any other programming language that you have used before? Have you done the file IO operations before? Any of you?
No.
No.
Okay. Are you aware how it is done? Have you studied how it is done? No? Okay. So the
No.
way it works is, you open a file and using a handle. There's something called a file handle. And you create a handle which points to, let's say, a text file. You create a handle to the text file and then you use that handle in your program to either read from the file or write to the file. Once all your read and write operations are over, then you close the handle. That's how file IO operations work. You create a handle and you point to the text file. Then using that handle, you read from the file or write to the file. Once your file IO operations are over, you close the handle. So this is file open to open the handle, F close to close the handle. Once it is open, all you have to do is use the handle name to read from it or write to it. And the other three system tasks, $F display, F strobe, and F monitor, are basically the same system tasks like $display, $strobe, and $monitor. The only difference is uh, basically we will read from a file and write to a file. In the $display system task, we were going to write to the simulation window. In $F display, we are going to write to the file, or you can use F write command also. So that will basically insert F display or F write will write formatted data to a file. F display and F write varies that they are same except F display, $F display inserts a new line after every execution, and $F write, not just write, F write does not. So if you want to write the contents or you want to write messages to, instead of a simulator window, you want to write it to a file, you use $F display. F display will automatically insert a new line character and go to the next line. If I use $F write, it will also write to the file. It will also write messages to the file, but it won't automatically insert a new line character and go to the new line. After F write, I have to always append it with backslash n. Backslash n will give me a new line character. Then we'll go to the new line. So fdisplay and fwrite will write to the file. Fstrobe will also write to the file. The only way fstrobe works is at the end of simulation it will write to the file, just like $strobe. Fmonitor will do the same thing like $monitor, that whenever a signal changes, arguments are signals. Whenever a signal changes value, instead of displaying it to the simulator window, it will display or write that particular message to the file that we have opened. So example for this is, let's say handle one. You can name it anything you want. This is just a text. Handle one is equal to $f open file name dot suffix. So file name dot suffix, it could be file name one dot txt for example. That's fine. If you do $f open my file dot txt, so handle one will point to my file dot txt. In using handle one, I can write to the file or read from it. Handle two is pointing to some other file. Now if I say $f handle one, which is pointing to file number one, format means I can put any format, %C, %D, %B for binary, D for decimal, H for hexadecimal. This variable list is the signal list. So I can write a list of signals to this file handle, which is pointing to file name one, using this format, %D, %H, or %B or anything. fstrobe will do it at the end of simulation. Fdisplay will do it whenever the fdisplay system task is called. Now this is pointing to handle number two, so file number two. Fwrite is similar to fdisplay. Only thing is new line character is not included. Uh, do you understand how this task will work? Fopen, F. Hello.
Yes.
Yeah. So maybe I'll give you time to note down this stuff and then we can go on system tasks. So whenever there are points you want to note down, you can note down.
I'm done.
Done with this,
Next
right?
slide, please. Yes. Next slide. I'm done.
Done with this.
I need a second. I'm done.
I'm done.
Me too.
done.
Okay, done.
I'm done.
Yeah. So this example, if we see this initial hash one, a equal to one, b equal to zero, dollar f strobe handle one. So handle one is pointing to the file name a comma b. So this is how it will be used. B equal to one. We'll write 1 1 for A and B. Why? Because F strobe is going to write the values of A and B at the end of simulation to the file. Initially A was 1, B was 0, but then later on B became 1. So towards end of simulation A was 1 and B was 1. So 1 and 1 was written for A and B in the file name pointed by the handle 1. That's how F strobe works here. It's just an example of how F strobe also works and handle 1 will also work pointing to handle. This is the next slide.
I'm done.
Done.
Me too.
Give me a second. Another.
Yeah, I'm done.
So that was about system task. We'll look about how to write test benches in Verilog. So when you write test benches, you can do various things with a test bench. In this section, how to write a test bench, how to create clocks. Although we have seen this, how to include file using the pre-compiler directives or compiler directives, strategic use of task and concurrent statements, controlling and observing the design, reporting any warnings and errors. So this is what a test bench is used for. So when you use a test bench, we have to declare a Verilog module to produce testing environment including stimulus generation and response monitoring. So DUT, this is your design under test, the main design. For any design, there are some inputs, there are some outputs. In the test bench itself is a Verilog design, Verilog code or Verilog module under which the design is instantiated. The design is instantiated and we apply the stimulus to the inputs of the design. Based on the stimulus of the inputs and based on the logic of the design, it will generate some outputs. This outputs is a response to the stimulus. And this stimulus, which is input to the design, and response, which is output of the design, both will be monitored at the test bench level. So we will generate timing diagrams for the input and the output of the design. The test bench applies the input, design generates outputs. Those outputs are again connected to local signals at the test bench level. So we monitor the inputs and the outputs, and based on the design, we analyze the timing diagram. Whether this, based on the inputs, whatever outputs are generated, whether they are correct or not. If they're correct, we say the design is functionally correct and functionally verified. If the response or the outputs are not correct, then we have to analyze where the error is. The error could be applying inputs to the design itself. The error could be in the input at the test bench level, or the inputs are correct, but the design is not generating the correct output. So you have to analyze if there is an error, where is the error, and fix the error. So this is the iterative process that we do. This is a general block diagram for the test bench or Verilog simulator. You have a Verilog design here. You have a test bench again in Verilog. Both are inputs to the simulator. You compile and simulate the design and the test bench. You look at the result and analyze this and fix any problems you have. So test benches are used for simulation and verification. We never synthesize the test bench, or we never implement the test bench on the chip. Could be FPGA, could be ASIC, doesn't matter. Test benches are meant for simulation purpose and verification purpose, so they will never be synthesized. So the most of the values will be applied from the initial block in the test bench. You can always have always blocks also, which are used normally for clock generations and some other inputs if required. Hash delays. Now, since test benches are not synthesizable, they are only meant for simulation purpose. All the Verilog language constructs are allowed in a test bench. For example, hash delay. Hash delay, just regular hash delay like hash 10, hash 20 is not allowed in a design directly. You have to work with clock signals for that. But in a test bench, since it's only we are going to only simulate the test bench. Hash delays and any other non-synthesizable constructs are allowed in the test bench. Dollar display and all of the system tasks we saw could be used, any of that could be used in the test bench. Then there is something called another directive, compiler directive called tick time scale, which defines a time unit. So we saw the tick time scale, then first is the time unit of the simulation followed by precision of the simulation. Now if we take this example here, top, so module top is where just a second, let me see. Yeah, okay. So the way this hierarchy works is I have a top test bench under which I have top design, which is the topmost level of my design is instantiated. And under top under of my design, again there are two modules or two blocks called A and B. Uh, this is the top level hierarchy. So this is the top level of my design. Under my design top, there is module A and module B. Two inputs go to module A, third input goes to module B. Final two outputs of module B are coming out as primary outputs. So anytime you have a design, the main inputs of the design and the main outputs of the design are called primary inputs and primary outputs for the design purpose. This module top is then instantiated in my test bench. This is my top test bench under which I am going to instantiate module top and I am going to make the connections for this. So module top is declared here. It is a gate. We are just creating the structure here where module A is instantiated, module B is instantiated, and we do the connections. This module top will then get instantiated at the test bench level. Under test bench, normally we apply inputs using the initial block. So applying a stimulus or inputs are applied through the initial block in the test bench. So how do we apply inputs to that? Let's assume A and B are two inputs. Initial begin A is equal to 0, B is equal to 0. Hash 10. So 10, let's assume the time unit is nanoseconds. So after 10 nanoseconds, I'm going to apply or change A is equal to 1. So A was 0, it got changed to 1 at 10 nanoseconds. Hash 20, so wait another 20 nanoseconds. Then make A equal to 0 again and B equal to 1. So at 10 A was 1. After another 20 means 10 plus 20 is 30. At 30 A will be 0, B will be 1 and the initial block. So this is how inputs will be applied through an initial block in the test bench. Now, if let's take another example. Now let's take this is a module called analysis. Let's not. I mean, this is a structural design, structural modeling. We're not going to details of the design itself. Let's say there are three inputs, A, B, and C. There are two outputs, F1, F2. I'm going to write a test bench for it. Always the test bench starts with tick time scale. Tick time scale 1 nanosecond slash 1 nanosecond. How do we read this? Take time scale 1 nanosecond. First value is the time scale or the simulation time that we're going to do, we're going to see is in nanosecond increments. So all the simulation time will increment in nanosecond format. And this is the second part is the precision. Means I can zoom the simulation maximum up to 1 nanosecond level. So I cannot go beyond that. I cannot go to picosecond level. So this is the second part is the precision. Then module test circuit. Remember that any test bench, it is always empty input output ports. Why? Because we need input output ports for for interaction with the external world. So you have a chip, let's say. Your chip is connected to the external world through input output ports. But your test bench itself is the external world here. So for that purpose, at a test bench level, you don't need separate input output. The test bench itself is the external world for the design. Now design here is analysis. If you see this module is analysis. My module called analysis is instantiated here. This is the instance label of the module. Then I'm doing the input output mappings. There is a reg called D, 3 bits. There are wires called F1, F2. So when you do this mapping at the test bench level, there are three inputs of the design A, B, and C. All the inputs will be mapped to local registers at the test bench level. And all the outputs coming from the design F1 and F2 will be mapped to local wires at the test bench level. Why registers at test bench level? Because I'm going to change the values. These input values will be changed. Once I change the value, then the ABC value will change. Internally, ABC value of the module will change. And based on the change inputs, I will get changed outputs from the design. So anytime you connect an input of a design, it should be connected to a register at a test bench level. The output coming back from the design can get connected to local wires or local nets because they are not going to get changed at test bench level. Design will drive that. The outputs are driven by the design. The test bench will just monitor them. Okay, so registers connected to inputs of the design under test and wires connected to outputs of the design under test. So I've done my instantiation, I've done my port mapping. Now I need to apply the inputs. So initial block is used for that. Initial, begin the initial block. D, now this is D 3-bit value, second bit, first bit and 0th bit are mapped to three different inputs of my module that is instantiated. So initial value of 3 0, 3 tick B 0 0 0. At a test bench level, I can use blocking assignments. I'm not worried about that because it's not going to go on the chip. At a test bench level, I can use blocking assignment. D is equal to 3 tick B, 3 tick binary value 0 0 0. Repeat 7. So I'm using a repeat loop here, which is going to repeat 7 times. Hash 10, D is equal to D plus 1. So every 10 nanosecond, 10 into 1 nanosecond. So every 10 nanosecond, D will be updated by 1. So it's an increment. We're going to, it's just a counter or we just increment D value by 1. Initial value of D is 0. We increment by 1, so it will be incremented 7 times. So from 0, 0, 0, it will be incremented 7 times using the repeat loop. Every time D is incremented or D is changed, automatically A, B, C is changed, which are inputs to the design. Since inputs are changed, your outputs will change based on what the design logic is. And this initial block. And we can have another initial block. So you can technically have two initial blocks also in the at the test bench level. The second initial block will show, or we can have dollar monitor here. Dollar monitor is a system task. What is it doing? Double quotes, parenthesis and double quotes. ABC is equal to percent %B. F1 is equal to F1 is equal to percent %B. F2 is equal to percent %B. So ABC 3-bit value displayed in binary format. F1 output value of the design displayed in binary format. F2 in binary format. And what are we displaying here? D. D is a 3-bit value. ABC will be displayed with the D value in binary format. F1 gets F1 value displayed in binary format. F2 gets F2 value displayed in binary format. Since this is dollar $monitor, anytime any of these changes, these are my arguments, D, F1, F2. Any of these changes, a new message will be displayed in the simulation window with the updated message and the updated value. End module. So we have written a test bench, instantiated my design, which we see here, done the port mappings for the input and output. Inputs are mapped to local registers, outputs are mapped to local wires. Why registers? Because I want to change their values, because I want to change the input values, and I want to try out different input combinations. Based on my input combination, the output will hopefully change based on the logic of the design. How do I change the inputs after doing the port mapping? I declare an initial block, change my inputs, initialize the input to some value and change my inputs as required. In this case, we are incrementing it by some time delays. End it. We use a dollar monitor to keep track of the input and the output values. So this message will be repeatedly displayed in the simulation window whenever any of this value changes, D or F1 or F2. End module. Do you understand this? Any questions you have for this? How test bench is written and used?
No.
No.
Okay, no questions. You can write this down. You can
No.
note it down. Um, this is a slide that probably will give you a good idea. So if you want an analogy of this, test bench software level testing, see, you might have used different boards, right? When you did your grad or undergrad. So when you have to test different designs or different boards on some design on a board, what did you do? You took a board which was behaving, which was having some logic. You applied some inputs to the board. How were the inputs applied to the board using some signal generators? Applying using some signal generator or some other software. And then the outputs from the board were connected to an oscilloscope or a logic analyzer. That's how you did it in actual hardware using boards. Now the same concept we want to use here. This is my board. Instead of a board, I have a design. Now to the design, I'm going to apply some inputs and I'm going to change the inputs. Based on the inputs and the logic of the design, some outputs will be generated. So I need to monitor now what is my design, what are my inputs. Based on this, these are the outputs. So are they correct or not? If they're correct, fine. I say functionally design is verified. If not, I need to find out where the problem is and I need to fix the problem. So that's an analogy with respect to a hardware based testing. The same concept we are implementing using a software level test bench approach. Okay, yeah, please go ahead with the.
I'm done.
Done.
Next slide.
Yeah.
Yeah, next slide, please.
Done.
Done.
Yeah, next slide, please.
I'm done.
Me too.
Yeah, let's just skip this slide because it's already covered in the other one. Yeah, so let's look at this example.
I'm done.
Done. Next slide.
Yep.
I'm done.
Done.
Yeah.
Okay, so we'll stop here today. We're going to see some other part of test bench writing next time. Uh, if you don't have Xilinx software installed, now is a good time to install it because next week will be practice time. We need a little bit of time next week's lecture, first lecture, for covering some remaining part of the test benches. But practically, you know how to write a test bench now. You already know how to do designs. You already have a few examples ready with you. So you should have your design and test benches. So let's try it out for a few couple of designs or maybe few of them. We can target combinational circuits initially, so you can write a design and a test bench both. So you should always write a design and a test bench combination. So two separate files, design file and test bench file for, let's say, a adder, a multiplexer 4 is to 1, a demultiplexer 1 is to 8, encoder 16 is to 4. You can try it out. Four designs: adder, 8-bit adder, 4 is to 1 multiplexer, 1 is to 8 demultiplexer, 16 to 4 encoder. Just a regular encoder, not a priority encoder. So these four designs there will be four. Each design there will be a separate Verilog file for the design and a separate file for the test bench. Okay. So next week's class, which is Monday, I will finish the remaining part of the test bench and I'll give you a demo how to simulate this design, how to generate a timing diagram, and how to analyze the timing diagram. If your designs are ready, you can try it out immediately after. Do you have
Okay.
Xilinx software installed on your PCs, or they are yet to be installed?
I need to install it.
Yeah, so go to Xilinx, go to xilinx.com. You have to create an account which is free of cost. Download the latest IC version, Xilinx ISE 14.7. That's the latest version. Then they will ask you for your network ID. So you just follow the procedure. It will be a license generated. It's free of cost, but it will have to be generated and it will be emailed to you automatically. You have to copy paste that license in the Xilinx software. Then it will work.
Okay.
Okay.
Yes.
So next class will be Monday, same time.
Okay.
Okay. Have a good weekend.
Thank you.
You too.
Thank you. Bye bye.